This lesson is going to talk about the basics of hypothesis testing. We're going to introduce the terminology and some of the concepts that go with it, and a little bit of the mechanics of it. The actual performing of a hypothesis test will be done in subsequent lessons. But for now, we're going to talk about what a hypothesis test is and how it works. So, a hypothesis is a claim or statement about a population parameter. For example, the claim that the mean human body temperature is 98.6 degrees Fahrenheit, or that mu is 98.6. This is a statement about the population that we don't actually know to be true. It's something that you might consider to be common knowledge, but it's something that, well, you might have always heard, but have you ever actually seen information to support that? Well, it's a claim. We might wish to test that by going out and collecting sample data. Another example of a claim is that the idea that more than 50% of consumers are not comfortable with drone deliveries for online order, or that P, the proportion, is greater than 0.5. Well, again, we don't really know that for sure. That's based on whatever Amazon or Etsy or whatever company stated. They might tell us, hey, most people are not comfortable with it, but we don't really know. So it's a claim that we may choose to test. The standard deviation is another parameter that we may see a claim about. For example, we may see a study that claims the IQ scores of college students has a standard deviation of 15, or that sigma equals 15. So all of these are claims, examples of claims about a population. But how do we actually know any of them are true? Maybe they're not. Maybe they are. Maybe we can find evidence against them, or maybe we can find evidence to support those claims. In any case, we would do a hypothesis test to test these claims and see if our evidence supports them or if our evidence does not support them. So, when we do a hypothesis test, we are always going to define two hypotheses. One of them is given to us in the claim. The other is a contradictory statement to it, so that we get two statements that literally claim opposite things. And therefore, we will make a decision to support one and reject the other, or support the second and reject the first. Now, the claim that's given to us may be either of these two hypotheses. They are called the null hypothesis and the alternative hypothesis. The null hypothesis, which is denoted H sub 0, is a statement that includes equality, an equals or perhaps a greater than equal or less than equal statement. Most often you will see equality, the actual equal sign, but many schools of thought will allow for the greater than equal to or less than equal to as well. The alternative hypothesis, which is denoted H sub 1, or if you look in our textbook, they use H sub A. Both are used and accepted notations, but either H sub 1 or H sub A. This is a contradictory statement to H sub O. It will always include the not equal to, greater than, or less than statement, respectively. That is to say, if the claim is that mu equals 98.6, then this would have to be the null hypothesis because it includes the statement of equality. And therefore, mu not equal to 98.6 is the alternative hypothesis. If, on the other hand, the claim is that p is greater than 0.50, this would be the alternative hypothesis. And therefore, the contradictory statement would be that p is less than or equal to 0.50. That would be the null hypothesis. So the statement given, the claim, may be either one of the hypotheses, and then from that we can define the other of the hypotheses. We always need both because we need contradictory statements so that when we make a decision about one, we automatically have a decision about the other. And the fact of the matter is that the test is always done on the null hypothesis. When we test, we are always testing the null hypothesis, whether the claim was the null hypothesis or whether the claim was the alternative hypothesis. Either way, we will always be testing the null hypothesis. The reason for this is that the null hypothesis is the one that includes the statement of equality. In fact, there are some schools of thought that only allow the null hypothesis to ever have the equal sign and does not allow for the greater than equal to or less than equal to. In any case, though, that statement of equality is important. Think about back in algebra class where you would see an equation versus an inequality to solve. The equation had definitive rules and definitive result that you got from it, whereas the inequality had, the rules were a little bit looser. Is a little bit more complicated to deal with. And the answer was much broader. It was a whole range of values, whereas the equation had a single distinct answer. For the same reason here, it's easier to work with the equality statement, and therefore we always test the null hypothesis. So when we do a hypothesis test and go through the procedure, at the end of it, we will make a conclusion as to whether we are going to reject the null hypothesis or whether we will fail to reject the null hypothesis. The implication is that if we reject H sub O, that we are therefore going to accept its contradictory statement, which is the alternative hypothesis. On the other hand, if we fail to reject the null hypothesis, then by default, we have to reject the alternative hypothesis. So one of these is going away, and the other will be kept. Now, why didn't we just say accept instead of fail to reject? I'll get to that in a moment. Let's talk about the possible combinations of decisions we can have. Our test can lead to a decision, but then there's an objective truth as well. That is to say, it's possible that the null hypothesis is, in reality, actually false, in which case we should reject it. That would be the correct decision. If you have a statement that's false, you should be throwing it away. On the other hand, if the null hypothesis is objectively true, then we should be keeping it. Now, the thing is that objective truth is really never known. The hypotheses are statements about a population parameter. And the fact of the matter is that it's rare, it's exceedingly rare, that we would ever know the value of a population parameter. If it's even possible at all. In most cases, it's simply not possible. That's the whole basis for doing things like confidence intervals. To say, well, I don't know for certain what the population mean is, but I'm pretty sure it's in this range of values. That objective truth as to whether the null hypothesis is true or false is actually pretty much never ever going to be known, which is why we're doing a hypothesis test to begin with. I mean, if we objectively were able to tell, yes, the null hypothesis is false, then we absolutely should make a decision to reject it. We don't even need to test it if we know the truth. The fact of the matter is we don't know the truth, and we never actually will. But these two correct decisions raise the possibility of mistakes, of incorrect decisions. There are two types of incorrect decisions, aptly named a type 1 error and a type 2 error. A type 1 error occurs when the test says we should reject the null hypothesis, but objectively the null hypothesis is actually correct. Well, we certainly don't want to reject a true statement, but since we don't objectively know whether it's true or not, we have to go by the results of our hypothesis test. So in that case, we would end up rejecting something that we should be believing, and that is a mistake. Of course, the other way, it's possible that objectively the null hypothesis is false, but our test does not lead us to that conclusion, and we fail to reject it. By all means, if it is false, we absolutely should be rejecting it, but our test doesn't lead us to that result. So these are the two types of errors that can occur, and we typically focus on the type 1 error because it is considered to be the worst of the two. An example of that might be in, say, our criminal justice system in this country. A person who is put on trial may actually have committed a crime or may not have committed the crime. And that objective truth is often not known. The trial then proceeds and the jury hands down a verdict to say guilty or not guilty. So first of all, let me point out the particular wording there. Not guilty or innocent, guilty or not guilty. Much like the phrasing that we have here, reject or fail to reject. Not reject or accept, reject or fail to reject. Guilty or not guilty. The idea is that there are two correct situations, that if a person actually did commit the crime, they are found guilty and then sent to prison. Or that if a person did not commit the crime, they are found not guilty. These would be objectively correct decisions. There is the possibility of two things that can occur, though, that are definitely not correct. It's possible that a person who did not commit the crime is found guilty and is sent to prison, or worse, and we send somebody who did not commit a crime to prison. That is considered to be definitely a bad thing in this country. The other situation is that the person actually did commit the crime, but the trial finds them not guilty. Now, this is definitely not ideal, but certainly it's considered worse to send an innocent man to prison than to let an objectively guilty man go free. And again, you have to look at the wording of it. Reject or guilty, these are definitive statements. I am rejecting this claim. I am saying this person is guilty. Versus fail to reject or not guilty. That's kind of like accepting, okay, I didn't quite get to the point that I needed to. I maybe wanted to reject, but I didn't quite get enough evidence to do so. And maybe I should have rejected, and maybe I shouldn't have, so I'm just going to leave it as not a strong conclusion. I'm going to leave it as I failed to reject. Or, again, maybe it's something that's like, okay, we know this person actually did it, but the evidence isn't conclusive enough. So it's like, okay, we're pretty sure they're guilty, but we got to pass down the not guilty verdict. We're not saying they're innocent. We're just saying we didn't find them guilty. So it's kind of like, almost like hedging your bet a little bit. But that definitive statement, reject the null hypothesis, that is a definitive statement So we want to be sure that if we're making that decision, we would like it to be a correct decision, if at all possible. So we're going to focus on the type 1 error and minimizing the chance of making that mistake. So let's set the stage here a little bit. We have a test that is being performed on the null hypothesis, which includes a claim of equality. Now, to test it, we're going to go out and collect a sample data. And then we're going to calculate our sample statistic. So let's suppose the claim is that the mean is 98.6 degrees. So we go out and we take the temperature of 20 people or 50 people or 100 people, whatever our sample is. And we take all of the temperatures of those people in the sample and we find the mean temperature. And suppose we find the mean temperature to be 98.3. Well, that definitely is not the 98.6 they claimed. But the question is it far enough off to say that 98.6 was wrong? Because it's always possible that we just got a sample of people whose body temperatures were a little lower. That's possible. So, it's definitely not 98.6, but the question is it far enough off to be able to say, oh no, that claim was definitely wrong? Or is it kind of like well, I'm not really sure. Well, the idea then, the decision is going to come based off of how much the sample data varies from the claimed data information, the claimed value. The question is, how significant is significantly enough? We have what's called a level of significance. The level of significance is the probability of committing a type 1 error, and we call that probability alpha. You might recognize alpha from when we did confidence intervals. And in fact, it is actually the same alpha. The confidence interval, remember, the confidence level was the area in the middle of the distribution. Alpha represented the area very, very far away from the center of the distribution, at the extreme sides of it, the extreme left and the extreme right. So that's where our type 1 error is. We want to know if our test statistic, if our sample data provided a value that was so significantly different that it was enough to say, nope, that claim was wrong. Now, the value of alpha is typically given for the purposes of this class. The value of alpha will be given in each problem. If you were out in the real world being a statistician and doing this kind of thing, you could choose the value of alpha you want, but the idea is that we want to keep it small. We want to keep it as small as we can because we don't want to make the error. We really want to avoid making it. So typical values for alpha are 0.01 or 0.05 or even 0.10, but you'll very, very, very rarely see anything bigger than 0.10. Even 0.10 itself is a little bit large because, again, we don't want to make the error. The idea then is that the smaller alpha is, the more extreme our data has to be to make the decision to reject. Remember, a type 1 error is rejecting a null hypothesis that is objectively true. We don't want that to happen. If it's objectively true, we don't want to reject it. We want to keep it. So by making alpha smaller, we're saying that the sample statistics have more wiggle room, that we are allowed to vary from the claimed value more and still believe the claim. This takes the form of one of three styles of tests. a left tail test, a right tail test, or a two-tail test. Now I'm going to use the normal distribution because it is a bell-shaped curve, and that is appropriate to both the normal and the t-distributions. The chi-squared distribution, as we saw for confidence intervals, is not a bell-shaped curve. So, and it works off of very slightly different principles, but the general concept of it is going to be the same. So, there are three types of tests depending on which, depending on what the nature of the hypotheses are, and where we're trying to see the extreme value. So, for example, suppose we are given a claim that the probability, that a proportion is less than 0.7. This would then be the alternative hypothesis, since it does not include the statement of equality, and therefore p being greater than 0.7 would be the null hypothesis. Whether we are doing a left tail test, a right tail test, or a two-tail test actually is indicated by which symbol is in the alternative hypothesis. A less than symbol in the alternative hypothesis indicates a left tail test. What that means is that somewhere out to the left side here, there is a critical value, a familiar term, again, from the confidence intervals chapter. And what we've got is a tail here, the area of which is equal to the value of alpha. And note that that is at the extreme left. So let's take a look at what our null hypothesis is saying, because we're testing the null hypothesis. The null hypothesis says that we should be getting a probability that is greater than 0.7. Greater than means we should be heading somewhere in this direction. The null hypothesis wants us to be over there. So if we find our test statistic is far off to the left, if our test statistic is far off to the left, it may suggest that the null hypothesis is incorrect. How far off to the left does it need to be? Well, it needs to be in the shaded region. We will talk about that shortly, but right now I'm just describing the idea of a left tail test. So, once again, our symbol of inequality in the alternative hypothesis is indicating a left tail test. Our null hypothesis wants our value to be bigger than 0.7. It wants it to be large. So if we find something that's very, very small, it might be enough to suggest that H sub O is wrong. A right tail test is used when the alternative hypothesis contains a greater than statement. So for this example, suppose we are told, we are given the claim that the population proportion is less than or equal to 0.25. This would be H sub 0 because of the statement of equality. Our contradictory statement then would be that P has got to be bigger than 0.25, and that would be our alternative hypothesis. Once again, we look at the inequality symbol in the alternative hypothesis, and this is what is going to indicate a right tail test. Very much the same as a left tail test, except this time everything's happening on the right side. So we will have some critical value, and beyond that critical value in this tail, that tail has an area equal to our level of significance. And again, if we look at what the statements of H sub O and H sub A are saying, H sub O wants us to have small. H sub O wants us to have a small probability. So if we find a large probability, if it's far enough off to the right, that might suggest that H sub O is incorrect. Ooh, excuse me. Got my words confused there. So that's the nature of a right tail test. If our null hypothesis is trying to get us to stay small, and our sample data comes out big, well, maybe H sub O is wrong. The question is it big enough? So note that there is actually a whole bunch of room off to the right side over here that is still valid. It's only if we get into that shaded region down there that we have to make our decision to reject H sub O. The last situation then is a two-tail test. A two-tail test occurs when we have a not equal to symbol in H sub A. So suppose we have the claim that our proportion is equal to 0.5. That's our null hypothesis then because of the statement of equality. Our alternative hypothesis then is P is not equal to 0.5. That not equal symbol indicates a two-tail test. The two-tail test, as the name suggests, is operating on both sides. But what that means, and this is more familiar to the confidence interval unit, it means that the area in the tails has to be split, or that the value of alpha has to be split between the tails. So the area in each tails is half of alpha. Now the concept of a two-tail test is based off of the idea that if H sub O says equal to, then we want it to be close to that. In this case, it's not about going left or right. In this case, H sub O is trying to be dead center. So if we vary too much to either side, that's enough. So if it varies too much to either side, it may suggest that H sub 0 is incorrect. So we need to know which kind of test we're dealing with. A left tail test or a right tail test or a two-tail test. And they are all indicated by which symbol is in the alternative hypothesis. Now, there are two approaches that we can take here. Rejection region or p-value. Personally, I prefer the rejection region method. I think it is a little bit more in line with what we did in confidence intervals. And I think it's also a little bit cleaner of an interpretation. But the p-value method is very often preferred. I think, in my experience, I think most statisticians tend to go with the p-value method. But as somebody who's teaching students, I think the rejection region method is a little bit easier to understand. The idea is that for the rejection region, that we're going to calculate our test statistic and convert it to a z-score or a t-score, depending on which distribution we're using. So we're going to calculate the test statistic, either x bar or p hat or s, the standard deviation, depending on which situation we're in. And we're going to convert it to a t-score, a t-value, a z-value, or a chi-squared value, respectively. We're then going to take the left tail, right tail, or two-tail test, and we're actually going to have to define the value of that critical value. So I'm drawing a left tail test, but it's easily adapted for the right or the two tail test. But the idea is we actually have to find this critical value. And that actually is done in the same way that we find the critical value for a confidence interval. The idea is that depending on the distribution that we're dealing with, a t, a z, or a chi-squared, we can find this critical value by using an inverse normal distribution, or an inverse t, or the t-table, or the chi-squared table. We can find out what that critical value is, or if it's a normal distribution, we can use the inverse normal command on the calculator. And then we have to see, where does our test statistic, once it's been converted to the appropriate value, does it fall into that shaded region or not? The idea is that that shaded region represents something that is far enough off from the claimed value to suggest strongly that the claimed value is incorrect. So if the test statistic falls in the shaded region, then we will reject H sub 0. That's how the rejection region works. And that's the method I'm going to primarily use because I think it's very clean. And again, the concept of finding that critical value is very closely related to what we did with confidence intervals. So it gives us something familiar to work off of. The p-value method is a little different, and I will explain that as an alternative when we actually see a problem, because I think it's harder to understand. The rejection region is easy to describe in a general sense like this. We can simply say, if the test statistic is in here, then reject H sub 0. But if our test statistic falls in here, then we fail to reject. Because it's off, but not far enough off. I think that's easier to describe in a general sense than the p-value method. The p-value method, I think, is much easier to understand when we see an actual example. So I'm going to hold off on the p-value method until the next lesson. Now, the last thing we really need to look at here is the conclusion statement. After we perform the test and make our decision as to whether we are rejecting or failing to reject the null hypothesis, there is a particular structure to the conclusion statement. There either is or is not sufficient evidence to support or reject the original claim. Now, whether we use is or is not, and whether we use the word support or reject, is going to be based on the nature of the hypotheses and the claim. So we use the word is or is not based on our decision on the null hypothesis. And then we determine whether we use the word support or reject based on whether the claim was the null hypothesis or whether it was the alternative hypothesis. Now that sounds really confusing, so an example is basically required here. So suppose we use the example that a claim is made that the mean human body temperature is 98.6 degrees. So that is our claim, and it is our null hypothesis that the mean is 98.6 degrees. That would, by default then, make our alternative hypothesis into the statement that mu is not equal to 98.6 degrees. This would then result in a two-tail test. And let's suppose that our sample data showed a very low, let's suppose our sample data shows a very low mean temperature. Now, how low does it need to be? Well, that depends on the level of significance that we allow for. I'm not going to get into the technical aspect of it right now, but suppose our sample data shows a very low mean and leads us to the conclusion or the decision to reject H sub O. Now, I forgot one important thing I want to mark here. That the original claim was the null hypothesis. So, we are rejecting the null hypothesis. That means that in our sentence, we're going to use the word is. Now, our original claim was the null hypothesis. So we are going to use the word reject. So what we are going to say here is that there is enough evidence or sufficient evidence to reject the claim that the mean is 98.6 degrees. So we have this claim, we do a hypothesis test, and suppose that our sample data shows a very low mean, and we make the decision to reject H sub O. So our sample data is providing evidence to say that H sub O is wrong. So there is enough evidence to reject the claim. When you actually have a situation like that, and you lay out what's going on with the claim and the two hypotheses and the decision, and you write the sentence, it clarifies this confusion up here. I understand that this is a particularly confusing bunch of phrasing here, but when you actually have a situation and you lay out what you've got, that statement will become much more clear, and you'll be able to see how it aligns with the test that you did. So again, the decision or the hypothesis testing here, this lesson is about establishing the core concepts of it. The next lesson we'll get into actually performing hypotheses tests. Until then, for now, the idea is to again focus on the terminology and the basic concept of it, deciding whether you want a left tail, a right tail, or a two-tail test, being able to make a conclusion, to write a conclusion statement based on what you're looking at, understanding what alpha is and how it figures into this, and why it is we're even talking about alpha, that we're trying to minimize the mistake of rejecting a hypothesis that really should have been true. So this is just about getting used to this stuff, and then next lesson, we will get into actually performing hypothesis tests on the mean and the standard deviation and population proportions.